Hey guys, welcome back to Saving Green. My name is Josh. Here on this channel, I do videos on ways to save money and the planet at the same time. And today we're going to visit the Honda Clarity, the daily driver that I use every day, and a car that I find to be very efficient, very practical, and just a great all-around driver. If you want to learn more about the vehicle, I have a whole playlist up here, which you can check out. But last November in 2020, I took a look at about 16 trips or so, and I wanted to determine how accurate the trip computer was in estimating how many miles I was able to achieve on a battery's charge. And that data revealed about 90% accuracy, give or take. And over the last year, I wanted to expand on that. I wanted to add a lot more trips over basically the whole year, give or take, and try to determine, well, not only is the trip computer still that accurate, but what other parameters might be worth looking into? Like, does temperature affect efficiency? Does the trip length affect efficiency? And is there really any difference between what the predicted and actual mileages are and what can influence that? But in order to kind of determine that, this is the method that I basically used. So first of all, I would reset my trip computer to 0, and then I would go about my day. Then I would record how many miles I was able to drive on that day, and I would compare that to how many miles were predicted at the start of that trip. And that ratio was going to be the percentage of accuracy, so to speak, of the predicted computer. Then I would plug my car in at night, and I would see how many kilowatt hours I was drawing from my house to charge that vehicle. And basically, that was my assumption as to how much battery power I used during the previous miles that I had driven. So let's say that I drove 15 miles over the previous trip. And then the next day, I checked overnight, and in the morning I realized that I plugged my vehicle in, and I got about 5 kilowatt hours drawn from the grid using my multimeter. Then I would say, okay, well, if I went 15 miles and I drew about 5 kilowatt hours from my home, then it took me about 3 miles per kilowatt hour on that particular trip. So that's kind of how I went through the analysis. And you can see here from the sample photo, this one picture kind of shows me not only the predicted mileage at any point in time, how many actual miles I've driven at up until that point, and the ambient temperature. So basically, the ambient temperature at the start of charging my vehicle is when I recorded that particular data set. And you can see here, basically on this page, kind of how those numbers are represented on this graph. You know, I have some information from all the way from the end of October of 2020 up until November of 2021. And I looked at a few different things. One is what the overall mileage was per trip. And a trip didn't necessarily mean every time I turned the car off and on. It was when I decided to charge my vehicle. Sometimes it was after just one day, so after 10, 12 miles. Sometimes it's after multiple days or after a complete charge cycle. And in the situations where I actually ran the battery to depletion, I basically recorded what the total mileage was at that particular time, temperature, etc. But then when the engine kicked in, I basically wasn't recording any data beyond that. So any additional mileage that the trip computer was recording, I did not include that in my analysis. So I really want to look at just all electrical, all battery mileage only. So basically, I started off using the odometer, and then later in my analysis, I basically reset the trip computer to 0 every time, so I got one more decimal place of precision. And I looked at the total kilowatt hours of every charge cycle. And we see that basically when I documented the miles and the predicted, what the ratio was, predicted versus actual, that's these percentages here. You can see sometimes I actually got more mileage than what was predicted. Those are values over 100%. And then the overall miles per kilowatt hour was basically looking at the total trip computer divided by how many miles I basically drove over the amount of kilowatts that I needed to replenish that particular charge cycle. And then the ambient temperature at the time of charging. So basically, when I scroll through all this data, I basically was able to divide it out into a few interesting subsets. So the first thing was looking at the predicted versus the actual mileage. And this was basically built off last year's analysis. So basically, the miles driven down here on the x-axis, and then the ratio of predicted to actual in the percentages. And basically what I wanted to do is I wanted to look at whether or not this line was more or less leveled at about 90%. And as we look at the overall efficiency here, we see that basically 93% is the overall, and if I go one more level of precision, 93.2 is the actual amount of predicted mileage that I was able to achieve overall. So that's important. And this was after 127 trips. It's not the full 145 because not all the data was complete for every day's worth of analysis. Now, what I also did is I looked at whether or not if I took shorter trips, let's say 20 miles or less, does that increase or decrease the accuracy? And in this case, it did. So if I took shorter trips, I got 96.4. This compared to about 97 from my previous studies. But what's interesting is that in the previous video, when I took out just the first half and the second half, I didn't do that this time. I looked at just the first 20 miles of those smaller trips, and those total I had 38. And then I looked at the longest trips, the ones where I drove more than 20 miles. I didn't necessarily divide the first and last half of the battery cycle because ultimately that was more difficult to do with this amount of trips overall. But it turns out that if I drove more than 20 miles, the predicted accuracy did drop to about 91.7. So I did a pair t-test, and I looked at whether or not those two populations of trips with fewer than 20 miles and those more than 20 miles, if those average accuracies were indeed significantly different, and in fact they were. I had a t-value of 0.019, which is less than the 5% threshold that we typically use in statistics. So it turns out that yes, there is a little bit more accuracy in shorter trips than longer trips when it comes to the predicted mileage, 96 and 92% respectively. Now, of course, the 92 was much better than the 78% I got in the last analysis. But that's because I was looking at the total trips this time and not just the second half of the battery cycle. So nonetheless, the predicted accuracy does drop most likely as mileage increases. So that was the first take home, which is that overall, the trip computer is about 93% accurate. The second thing is I looked at temperature. So the overall average temperature coincidentally happened to be about 80 degrees from this year's worth of data in South Florida. Coincidentally, 80 degrees is the cutoff that I use whether or not I'm going to turn the AC on or not. I typically turn the AC on if the temperature is greater than 80 degrees, and I typically leave it off and put the windows down if it's less than 80 degrees. So again, for this particular thing, I trended out the efficiency in miles per kilowatt hour here on the y-axis, and then the degrees here in the x-axis. And we see that yes, there is a negative relationship. So the efficiency does decrease as temperature goes up. And again, while this is linear data, you can see that the correlation here in terms of R squared is not that correlated. It's about 0.18. Nonetheless, I wanted to see, well, again, do those populations of data actually represent any significant change in efficiency? And as it turns out, they do. So basically, the overall average efficiency total from 140 trips that I was able to get this particular set of data from, I had 2.9 miles per kilowatt hour overall for all these trips, which again is higher than last year's data. Now, if I parse that out into those 57 trips where the temperature was less than 80 degrees, 79 or less, my efficiency goes up to 3.1. And if I divide the population of trips of 80 degrees or higher, the efficiency drops to 2.7. And again, a very significant difference here of a t-value far less than 5%, suggesting that yes, these populations of efficiency data is in fact different. So this t-test did show that the air conditioning usage does negatively impact the driving efficiency significantly. And again, just to double check, I looked at the variances as well, these populations, and they were more or less equal, so I knew which type of t-test to use in this situation. And then the last set of data that I want to look at specifically was the overall efficiency versus the overall trip length. In other words, if I drive more, does my efficiency drop off? Not just does the predicted mileage drop off, but does the efficiency itself drop? And here again, I look at trips less than 20 miles and those greater than 20 miles. Again, I had 137 trips in this particular data set. And again, 2.9, 2.93, very similar to my previous averages in terms of the overall efficiency in miles per kilowatt hour here. And again, similarly, if I look at the overall trips, the efficiency of 2.9 for those less than 20. And coincidentally and interestingly, the efficiency was higher for the longer trips here, 2.95 miles per kilowatt hour. This is different than the predicted mileage. This is the actual efficiency of the battery. So in other words, does the battery itself lose efficacy or efficiency over longer trips? It actually doesn't. In fact, this was not a significant t-test value of 0.47, so only much greater than the 5% threshold that we typically need to suggest differences among these populations. So nonetheless, it did not pan out to be so. The overall efficiency was actually fairly stable, no matter the duration of the trip, which I found really interesting. And here we see that this is almost a straight horizontal line, as I increase my mileage, yes, the trend line does suggest a slight positive trend. So the efficiency technically does increase a little bit over longer trips, which I thought was interesting. But again, not a significant relationship here. The R-squared correlation is very, very small at 0.023. So again, nothing really to write home about. So what did we learn? Well, we learned that overall, over this year's worth of data, the most important contributor to loss of efficiency is temperature and therefore air conditioning usage. I imagine it's similar if you're running the heater in very, very cold environments as well. Now, certainly these batteries do lose some efficiency below a certain degree. So we know that all battery engines do lose some efficiency in really, really cold environments. Wasn't the case here in South Florida in Delray Beach with an average temperature of about 80 degrees, but nonetheless, those are kind of the take homes. So once again, if we kind of, pan out a little bit, we can look at what the summaries of the data suggest. So one is that the overall predicted mileage was about 46 in total with a standard deviation of about 3.3. I charge my vehicle for a total of about 9.8 kilowatt hours every charge cycle. Standard deviation about 3.4. Again, the capacity of my particular battery is about 14.8 kilowatt hours running it to depletion. My average trip was about 28 miles with a standard deviation of about 9.9. The predicted versus true mileage achieved was about 92% with a deviation of about 10 or 12%. And my average kilowatt hours was about 2.9 miles per kilowatt hour with a standard deviation of about 0.47 with an average temperature of about 80 degrees with a range of 7.7. And again, I recorded data all the way from 94 degrees down to about 53, which is the coldest reading here in Florida during this particular set of drives. So that's that. Overall, the Clarity is a very efficient vehicle. It holds up over short and long periods of time, which is different than what I thought initially. And I was getting better overall real-world driving efficiency of about 2.9 miles per kilowatt hour than I thought that I had last year, which was down to about 2.5. And of course, the biggest take home as far as statistical significance was the use of air conditioning. So guys, thank you so much for checking out the video. I hope that it was interesting. If you have your own analysis on the Honda Clarity or other electric vehicles and maybe have run your own numbers as what the efficiency truly is, I know that that would be really good to know. The Honda Clarity doesn't provide any actual efficiency statistics the way the Teslas do, but I'm curious if the real world driving is accurate to what the Teslas are predicting, just as we found that the predicted mileage on the Honda Clarity is not totally accurate in this particular situation. So please comment with any insight that you guys have into this analysis. If you have any corrections or if you think that I should have used different statistical tests, I'm certainly open to learn about what you think might be most appropriate. So hit that like button, it really helps the channel grow, and consider subscribing if you found this information helpful. I'll talk to you soon, and I'll see you in the next video.